Hi, welcome to this first video for the Stage 1 chemistry topic of acids and bases. This says topic 5. For my students, you'll notice we're doing this as the third topic. I just think that's where it fits a little bit better. But if you are looking at the SACE curriculum outline for Stage 1 chemistry, this is topic number 5. As always, for my videos, I do have a embedded YouTube videos throughout the PowerPoint here. So if you would like a copy of this PowerPoint, if you're not one of my students, you can always email me. My email address is at the top here. It's bill.stapleton884@schools.sa.edu.au. More than happy to share you a link where you can download this or any of the PowerPoints. So anyway, you do see through the PowerPoint here one of these YouTube symbols. You can click on that and it will take you directly to one of the other videos, which gives you a bit more in-depth explanation than what I give in this video. Alright, so we're going to look at some acid-base concepts. This is subtopic 5.1, and we're going to be looking at just a brief introduction to, I guess, the acid-base theory. So what is an acid, what is a base? We're going to be looking a little bit at some of the properties of acids and bases, some of the ways they react, and I'll just have a brief introduction to what conjugate acid-base pairs are as well. So it's important when you understand about acids that you're going to hear the term proton a lot. Now, when you think of proton, you probably think of, something inside the nucleus, something small with a positive charge, and that's correct. That's what a proton is. But when we're talking about a proton in terms of acid and bases, we're talking about a hydrogen ion. So a hydrogen atom here is this. So it's got one proton, no neutrons in the nucleus, and it's got one electron orbiting around it. So its atomic number is 1, its mass number is 1. When that hydrogen loses this electron here, okay, it now only becomes one proton. So a H plus is in fact just a proton. So that's what we're going to be using interchangeably here. So when we're talking about protons, and you'll see why we're talking about protons in a minute, we're actually referring to a H plus ion over here. Okay, so it's important you understand that as we get started. So if you want to know what an acid is a substance that donates protons. That means it's a substance that donates H plus. Okay. And conversely, a base is something that accepts protons, okay? So you've got this reaction that occurs and this balance between an acid and a base, where an acid donates the proton and then the base accepts that proton, all right? So there's that transfer of a H+, and that's really what defines an acid-base reaction. Now, some of the properties of acids and bases, all right, you might have seen a scale like this before. All right, this is called the pH scale, and it ranges from 1 to 14. Okay, now on the pH scale, everything below 7 is considered acidic. So these colours here, all right, all the way down to 1, 1, 2, 3, 4, 5, 6, these are all considered acidic pHs, okay? So if you're trying to remember what colour is associated with acids and what colour is associated with bases, I always say to my students, remember about if you get an acid on you, if you know about acids, they burn, okay? And so it's the hot colours, the warm colours, all right? So the yellows, the oranges and the reds, they're your colours for acids. Whereas bases, on the other hand, are the cooler colours, okay? So the green, the blues, and they're the colours you get when you're looking at a base. We've got some common things here on the pH scale, okay? So gastric acid, your stomach, actually has hydrochloric acid in there. Now, hydrochloric acid is something that's called a strong acid, and I'm going to explain what a strong acid means in a little bit. Okay, but it's very good at breaking down the food that you eat, all right, really important. So that's a really strong acid, has a really low pH. Then you got to some things like apple juice, tomato juice, coffee, they are all slightly acidic. Lemon juice here, which is acetic acid, they're slightly acidic. And then you get over here into things that are quite basic, all right? So you've got eggs, baking soda, hand soap. At the time of recording this, we're still dealing with coronavirus. And so they're saying the best thing you can do is wash your hands with hand soap. Hand soap is slightly basic, or what we call alkaline. And alkali is a water-soluble base. That's really good at dissolving the fat coating around the coronavirus particle, and that helps to destroy it. So having a basic solution like hand soap is really, really good. Then you get into things which are more basic, like bleaches and concentrated solutions of alkalis, okay? So that's the pH scale. We're going to be talking about that a lot, and we're going to look at that particularly with indicators in the next video for this topic. But for now, what I'm going to just talk about is just where you can find some acids and bases at home. So common acids you'll find at home: vinegar, citric acid, lactic acid, ascorbic acid, okay? So ascorbic acid is a really good one at the moment, particularly heading into winter. Really encourage you to take your vitamin C, help keep your immune system up, help fight off diseases and viruses, which is really important, okay? Then you've got things like citric acid, which is found in citrus fruit, so things like oranges and lemons. Okay, lactic acid found in milk. All of these are what we call organic acids, and I'll explain about organic acids in a couple of slides' time. But basically, they're ones that are made up of only carbon, hydrogen, and oxygen, and they're all weak acids, which are really good because you don't want to have really strong acids around the home. Some of the bases you can find: baking soda. This is sometimes called bicarb soda, often used in cooking. Okay, and it's used as toothpaste. It's really good abrasive, so it helps to actually take off stuff on the surface of your teeth, which is really good. So when you brush, you're brushing with some baking soda in there, and it helps you just clean your teeth really nicely. Borax is a cleaning agent. If you've ever come across little tubs of something called gumption, that is borax. That's quite good for cleaning. Milk of magnesia is a laxative, so hopefully you never have to take that. And then you've got things like ammonia, which is a really, really good cleaning agent that has a very characteristic like a cat wee smell, so it's not pleasant at all, but it's a really good cleaning agent because it's a good base. And then you've got lye, which we more commonly call caustic soda. That's really good as an oven and drain cleaner. So you might have seen parents or someone putting crystals down a drain. That's actually sodium hydroxide crystals, really good at dissolving fats and greases and oils that are in drains and clog them up. Now, the whole theory of acids and bases, that whole theory that acids are proton donors and bases are proton acceptors, came about in 1923 from two chemists, Bronsted and Lowry, and they developed that theory that we still use today. Okay, the bases, though, however, have been around for thousands of years, and people have always known that things like lemon juice and vinegar were known to be acidic, and that raw milk, including things like buttermilk, are slightly basic. Okay, so it's been quite commonly known for a long time that you know, if you got stung by certain insects, that you could treat them by using something of the opposite acidity or basicity. So ant bites or stings, bee stings, for example, you could actually treat them using something that would help neutralize the sting. So I've talked a little bit about strong or weak acids, and I want to just take a little bit of a moment so you can understand what we mean by that. So if you understand that definition, that a acid is a proton donor, not all acids donate H+, a proton, as readily as others. So some of them donate it really readily. They're the ones that are very strong. Okay, so things like sulfuric acid, hydrochloric acid, nitric acid, they donate their hydrogen really readily. What that means is they will give it up very quickly in a reaction. Okay, whereas other acids, like those ones we talked about at home, they're weak acids. So vinegar is a really good example. That doesn't readily donate its proton. So that's what we call a weak acid. Now that is different from the term concentrated and dilute. And concentrated and dilute purely refers to the amount of water that is present. So I always refer to cordial when I'm trying to explain this. My favorite cordial growing up was this Cooler cordial. I'm not sure if you guys ever had it, but it was just amazing. I loved it. Every time in summer I can just remember coming inside and having a cool glass of this. It was really good. Love if you guys want to comment down below what your favorite cordial was or is. Love to know if there's anyone out there who loved Cooler as much as me. But let's say, for example, you're an absolute mad lad and you decided that you would just pour this cordial straight out of the jug here into a glass, and then you put maybe like a couple of drops of water in there. Okay, that is a super concentrated glass of cordial. Okay, and that's exactly the same for acids and bases. Okay, when you have a lot of the acid there and only a small amount of water, that's concentrated. Let's say you go to the other extreme and you're one of those other people that puts like 2 drops of cordial in and then fills it up, so that all you've got is basically a glass of water that might have a very pale color to it. Okay, that's very weak. Okay, all right, that's a very weak cordial. Right, you can hardly taste the cordial, you hardly notice it's there. That's the same with acids and bases. If it's a weak acid or base, okay, there's only a very small amount of there and there's a large volume of water. So it's important to understand you can have concentrated weak acids, okay, and you can have dilute strong acids. Okay, it all comes down to how readily it donates its proton. That defers if it's strong or weak, and how readily, how much water there is. That refers to if it's concentrated or dilute. Now, sorry, I know I just realized I referred to when there's a small amount of cordial in there and a lot of water. I called that weak. Sorry, that should have been dilute. So when there's a small amount of cordial, lots of water, that's dilute. Okay, I have done a video up on this which will probably explain it way better than what I've just done now. Okay, so look at this video here. It's called Acid Strength and Concentration. You'll find it on this YouTube channel if you want a bit more information. So the most common reaction that acids and bases occur is what's called this neutralization reaction. So when you have an acid and a base, it gives you salt plus water, and that is the generic reaction for acids and bases. So I've got some examples here of hydrochloric acid with sodium hydroxide giving us sodium chloride and water. So this is our salt. Okay, and there's our water. Same for this one, sulfuric acid, calcium hydroxide, and then we've got vinegar here, acetic acid plus sodium bicarb. This one, because it's a bicarbonate, we've still got an acid-base reaction occurring, but because it's a carbonate, we also get carbon dioxide gas given off. Now, the reason I call this same but different is because we can actually write all three of these equations exactly the same way. And it comes back down to that definition of acids and bases I introduced you at the start of this video. The acids are proton donors and bases are proton acceptors, okay? So in each of this case, we've got a proton here, we've got a proton here, and we've got a proton here. All three of these acids are donating a proton. Here, these bases are accepting the proton, and in particular, there's always something in the base that accepts that proton, and it reacts to form water. So the actual acid-base reaction, any acid-base reaction, could be written this way: a hydrogen ion from the acid is attracted to hydroxide ion from the base, an OH, and that forms water. This is called an ionic equation, so we're just showing the ions that are involved. We're not showing the other ions that aren't involved. They're called the spectator ions. So it doesn't matter what acid we're using. If we go back to this one, hydrochloric acid or sulfuric acid or vinegar, it doesn't matter. We still end up with water as the product. We still get the hydrogen donated from the acid and the base accepting the proton, and we get water forming. So this reversible reaction, it's reversible because it's got these equilibrium arrows in there. That's a whole different topic, but that's what those mean. It can go both ways, okay? This is the general reaction, an ionic equation for an acid-base reaction. So when we're talking about doing reactions with acids, we don't have to specify if it's sulfuric acid, nitric acid, vinegar, whatever, okay? We can just use H+ to represent our acid, okay? Because it's always the same reaction. Now, something that you get when you get acid-base reactions is what's called conjugate acids and bases. Okay, so conjugate means together or joined. So a conjugate acid is a species formed from the base accepting a proton. So what do I mean by that? We'll have a look at the hydrochloric acid here. This is an acid because it can donate a proton. So this hydrogen gets donated to the base, the ammonia. What we end up with once that hydrogen is gone is a chloride ion, Cl-. Now that Cl- could actually accept a hydrogen. Okay, if that accepted a hydrogen, it would form HCl. So that's why it's a base. Okay. Conversely, this base here, ammonia, NH3, that accepts a proton to form the ammonium ion NH4+. But that NH4+ could actually donate a proton, acting as an acid, to reform a base. Now, conjugate acid or base are weaker than the original acid or base they started from. So this is not a good base. This is not a good acid. Okay. These are much stronger acids and bases. So this more readily donates a proton, this more readily accepts it. Okay, this does not readily accept it, this is not readily donate it. So that's what the whole conjugate acid-base pair is all about. Final thing I'm going to talk to you about is just what we refer to in terms of number of protons that an acid can have. Okay, so acids that have one proton are called monoprotic. So mono means one, protic means proton. So these pink ones here all have one hydrogen here that they can donate. These ones here, sulfuric acid and carbonic acid, they both have two protons to donate, so they're called diprotics. That they can actually do two reactions, two steps in the reaction. This one here, phosphoric acid, actually is a triprotic. It has three protons, and that can actually donate a proton 3 times. So that's what we mean by triprotic. Alright, this has been a little bit longer than I normally like to do for these, but there was just a bit to go through and cover. So hopefully you've got a fair bit out of this. The main things to remember: acids are proton donors, bases are proton acceptors. That's the real key thing to take out of this video. Okay, a proton is a H+ ion. And then probably the other thing to really take out is about strong versus weak acids. So that's how readily they donate a proton, and concentrated versus dilute. Alright, hope this has been fairly straightforward to follow. Please make any comments below if you've got any questions, anything you want. Please hit subscribe. And as always, stay safe and look after yourselves. Thanks, guys.